We think we know what the universe is made of. Stars, planets, gas, dust. The stuff we can see. The stuff we are made of. Atoms. Protons, neutrons, electrons. It all seems solid. Real. It's what we call normal matter. But it turns out all of that, everything we have ever seen or touched or measured, is just a tiny fraction of what's out there. About 5%, the rest is a mystery. A huge chunk of it, about 27%, is something we call dark matter. We know it's there. The evidence is overwhelming. We just have no idea what it is. It's not just dark, it's invisible, it doesn't shine, it doesn't reflect light, it doesn't block light. It seems to pass right through us, right through the Earth, right through everything, as if it weren't there at all. Except it is. It has mass, and because it has mass, it has gravity, and that gravity is the only reason we know it exists. It's the ghost in the machine, the invisible hand that shapes the cosmos. It's the scaffolding upon which our entire universe is built. Without it, there would be no galaxies, no stars, no us. So what is it really? That's one of the biggest questions in all of science. It's a detective story that started almost a century ago, and we still haven't found the culprit. The first clue came from a man who was famously difficult. His name was Fritz Zwicky. He was a brilliant, abrasive astronomer working at Caltech in the 1930s. He called his colleagues spherical bastards because he said they were bastards no matter which way you looked at them. He was not a popular man, but he was a careful observer. Zwicky was studying a huge collection of galaxies called the Coma Cluster. It's a swarm of over 1,000 galaxies, all bound together by their mutual gravity. He was trying to figure out how much the cluster weighed. He did it in two ways. First, he looked at how much light the galaxies were putting out. More light, more stars. More stars, more mass. This gave him one estimate for the cluster's total mass. Then, he did it another way. He measured how fast the galaxies on the edge of the cluster were moving. If the cluster was held together by gravity, then the galaxies couldn't be moving too fast. If they were, they would fly off into space like a rock let go from a slingshot. The speed of the outer galaxies tells you how much gravity, and therefore how much mass, is in the cluster holding them in. And here was the problem. The two numbers didn't match. They didn't even come close. The galaxies were moving way too fast. Based on the gravity needed to keep them from flying apart, the cluster had to have over 400 times more mass than what he could see from its starlight. It was a stunning discrepancy. Zwicky was confident in his observations. He concluded there had to be a huge amount of unseen matter in the cluster. He called it dunkle materie, dark matter. For the most part, the scientific community ignored him. His calculations were a bit off. His personality didn't help. The idea was too strange. Missing matter, hundreds of times more than visible matter. It seemed like a mistake. The idea of dark matter faded into the background for decades. Then came Vera Rubin. In the 1960s and 70s, Rubin was an astronomer at the Carnegie Institution in Washington. She was a meticulous and persistent scientist working in a field dominated by men. She decided to study the rotation of individual galaxies, specifically our neighbor, the Andromeda Galaxy. Think about our solar system. Mercury, the closest planet to the sun, whips around at high speed. Earth moves at a more leisurely pace. Neptune, way out on the edge, crawls along. The farther you get from the central mass, the sun, the slower you go. That's just basic Newtonian gravity. A galaxy should work the same way. Most of a galaxy's visible mass, the stars and gas, is concentrated in the bright central bulge. So stars near the center should move fast. Stars farther out, on the dim edges of the spiral arms, should be moving much, much slower. They are far from the bulk of the mass. Rubin and her colleague Kent Ford developed new, highly sensitive instruments to measure the speed of stars at different distances from the galactic center. They pointed their telescope at Andromeda and started taking data. What they found made no sense. The stars near the center moved fast, as expected, but the stars farther out didn't slow down. They just kept on moving at the same high speed, all the way to the visible edge of the galaxy. It was like Neptune was moving as fast as Mercury. This flat rotation curve, as it came to be called, was impossible. The outer stars were moving so fast they should have been flung off into intergalactic space millions of years ago. The galaxy should have torn itself apart, unless the galaxy was embedded in a massive, invisible halo of something else. Something that didn't shine, something that spread out far beyond the visible stars. This halo of dark matter would provide the extra gravity needed to hold the fast-moving outer stars in their orbits. Rubin and Ford didn't want to jump to conclusions. They thought it might be a fluke. So they looked at another galaxy, same result. And another. And another. Every single spiral galaxy they looked at had a flat rotation curve. Every single one was spinning too fast. Every single one seemed to be held together by a huge amount of invisible matter. This time, people listened. Vera Rubin's data was too clean, too consistent to ignore. Fritz Zwicky had been right all along. The evidence was now undeniable. Our universe was mostly invisible. Dark matter wasn't a niche, strange idea anymore. It became a central problem in cosmology. But the evidence didn't stop there. It started pouring in from other areas of astronomy. One of the most powerful tools for seeing the invisible is something Einstein predicted called gravitational lensing. The idea is simple. Mass warp spacetime. Think of spacetime as a stretched rubber sheet. If you put a bowling ball on it, it creates a dip. If you then roll a marble past the bowling ball, its path will be curved by that dip. This light works the same way. The path of light is bent when it passes by a massive object. A huge cluster of galaxies can act like a giant lens, a cosmic magnifying glass, bending and distorting the light from more distant galaxies behind it. By looking at how much the light is distorted, astronomers can calculate the mass of the lens, the galaxy cluster. And just like Zwicky found, the mass required to produce the lensing effect we see is far greater than the mass of all the visible stars and gas in the cluster. Usually, it's about 5 or 6 times more. That extra mass is dark matter. We can't see the dark matter itself, but we can see the effect of its gravity on the light passing through it. We are seeing its shadow cast in the fabric of spacetime. Then came the smoking gun evidence. This is the bullet cluster. This is actually 2 galaxy clusters that collided, or more accurately, passed through each other like ghosts. It's a perfect natural experiment. When the 2 clusters collided, the normal matter, which is mostly huge clouds of hot gas, crashed into itself. The gas clouds from each cluster slammed into each other, slowed down, and got stuck in the middle, glowing brightly in X-rays. But what about the dark matter? Since dark matter doesn't seem to interact with anything except through gravity, the dark matter halos of each cluster should have just passed right through each other without slowing down. Astronomers used gravitational lensing to map out where the mass in the bullet cluster was. They found 2 big clumps of mass, and those clumps were not in the middle with the hot gas. They were on either side, having sailed straight through the collision unscathed. The vast majority of the mass, the dark matter, was completely separated from the normal matter. This was a huge deal. It showed that dark matter is a real substance, not just some weird modification of gravity. Whatever it is, it doesn't bump into normal matter. It doesn't feel friction. It just keeps on going, pulled only by its own gravity. The final, and perhaps most profound, piece of evidence comes from the very beginning of the universe. It comes from the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a baby picture of the universe when it was only about 380,000 years old. This picture isn't uniform. It's covered in tiny temperature fluctuations, tiny hot and cold spots. These spots were the seeds of all future structure. The slightly denser, slightly cooler spots had more gravity, and over billions of years they pulled in more and more matter to become the galaxies and galaxy clusters we see today. Scientists have built a stunningly precise model of the universe called the Lambda CDM model that can explain the exact pattern of these spots in the CMB. It works incredibly well, but it only works if you put in the right ingredients. And those ingredients are very specific. The model requires the universe to be about 5% normal matter, 27% dark matter, and 68% dark energy, which is a whole other mystery. If you try to build a universe without dark matter, it just doesn't work. The gravity from normal matter alone isn't strong enough to form galaxies as quickly as they did. The universe would look completely different. The CMB tells us that dark matter was there from the very beginning, providing the gravitational scaffolding for everything else to build on. So, the evidence is solid. Dark matter is real, but that just brings us back to the original question. What is it? We can start by ruling things out. Could it just be normal stuff that's dark? Things like burnt-out stars, cold gas clouds, or rogue planets floating between galaxies. These are sometimes called machos for massive astrophysical compact halo objects. For a while, this was a popular idea, but we've looked hard. If a macho passes in front of a distant star, its gravity should act as a mini lens, making the star briefly appear brighter. This effect is called microlensing. Astronomers have done massive surveys monitoring millions of stars for years looking for these events. They found some, confirming that things like rogue planets exist, but they didn't find nearly enough to account for all the missing mass. Not even close. So dark matter is not made of normal matter, it has to be something new. Something not made of protons, neutrons, or electrons. Something exotic. Could it be neutrinos? We know neutrinos exist. Trillions of them are passing through your body every second. They have a tiny bit of mass and they barely interact with anything. They sound like a perfect candidate. But there's a problem. Neutrinos are hot, dark matter. That means they were moving at near the speed of light in the early universe. Because they were moving so fast, they would have tended to smooth out the small density fluctuations. They would have prevented the small clumps from forming that later grew into galaxies. Our universe, with its intricate web of galaxies, could not have been formed with hot, dark matter. We need cold, dark matter, something that was moving slowly in the early universe, allowing small structures to clump together first. So we need a new particle, something not in the standard model of particle physics, our current best theory of fundamental particles and forces. This is where the hunt really begins. For decades, the leading candidate was a hypothetical particle called the WIMP. WIMP stands for Weakly Interacting Massive Particle. The name says it all. It's massive, so it has plenty of gravity. And it's weakly interacting, meaning it rarely bumps into normal matter, which is why we haven't seen it. The WIMP was a beautiful idea, especially in the 1980s and 90s. Physicists were already working on theories beyond the standard model, like supersymmetry, which tried to unify the fundamental forces. These theories naturally predicted the existence of new, heavy, stable particles that didn't interact very much. The properties of these predicted particles matched the properties needed for dark matter almost perfectly. It was called the WIMP miracle. It seemed like the solution to two huge problems at once. Dark matter was a clue pointing to a deeper, more complete theory of physics. This kicked off a massive worldwide search for WIMPs. The search is happening on three fronts. The first is direct detection. The idea is to build a detector, put it deep underground, and wait for a WIMP to hit it. You have to go deep underground, often in old mines, to shield the experiment from all the other particles, like cosmic rays, that are constantly bombarding the Earth's surface. These detectors are incredibly sensitive. They're often vats of super pure liquid like xenon or argon cooled to extremely low temperatures. If a WIMP from the galaxy's dark matter halo happens to fly through the detector and bumps into the nucleus of one of the xenon atoms, it should create a tiny flash of light or a tiny vibration. It is an unbelievably difficult experiment. It's like trying to hear a single feather drop in the middle of a rock concert. Dozens of these experiments have been built and run. Exanon 1T, LUX, PandaX, they have gotten bigger and more sensitive over the years. And they have all found the same thing. Nothing. Not a single unambiguous WIMP signal. The experiments have now ruled out huge swaths of the territory where the most popular WIMP theories predicted we should find them. This doesn't mean WIMPs don't exist. They could be lighter or heavier or interact even more weakly than we thought. But the fact that we haven't found them where we most expected to is a big problem. The WIMP miracle is looking less and less miraculous. The second front is indirect detection. If WIMPs exist, they should be concentrated in the centers of galaxies, including our own Milky Way, where gravity is strongest. Sometimes, two WIMPs might run into each other and annihilate, destroying each other in a burst of energy and creating other, more familiar particles like gamma rays or neutrinos. So, we can use telescopes to look for an excess of these particles coming from places where we expect dark matter to be dense. We have pointed gamma ray telescopes like the Fermi Space Telescope at the center of our galaxy. We have used neutrino detectors buried in the Antarctic ice, like IceCube, to do the same. There have been some tantalizing hints. A few years ago, there was excitement about an excess of gamma rays from the galactic center that seemed to match what a WIMP signal might look like. But further analysis suggests it could also be coming from more mundane sources, like thousands of rapidly spinning pulsars. As with direct detection, there's no smoking gun. The third front is trying to make dark matter here on Earth. That's one of the goals of the Large Hadron Collider, or LHC, in Switzerland. The LHC smashes protons together at enormous energies to recreate the conditions of the early universe. The hope is that in some of these collisions, we might create a pair of dark matter particles. Since they are weakly interacting, they would fly out of the detector without leaving a trace. We couldn't see them directly, but we could infer their existence. If the particles flying out of the collision are all going in one direction, it means something invisible must have shot out in the opposite direction to balance the momentum. We would see it as missing energy. So far, the LHC has found the Higgs boson, but it hasn't found any evidence for supersymmetry or any unexpected missing energy that would point to WIMPs. The WIMP is not dead, but it's in trouble. The null results from all three fronts have forced physicists to look more seriously at other possibilities. The field has opened up. One of the most promising alternatives is a particle called the axion. Actions are completely different from WIMPs. They are predicted to be incredibly light, billions or even trillions of times lighter than an electron. They were not invented to be dark matter. They were proposed back in the 1970s to solve a completely different problem in particle physics called the strong CP problem. The fact that they could also be dark matter is an elegant bonus. If axions exist, the universe is filled with a sea of them, like a vast, invisible wave. Its experiments are now being built to try and detect this wave. The leading idea is that in the presence of a very strong magnetic field, an axion can sometimes turn into a photon, a particle of light. So, experiments like ADMX use a powerful magnet inside a refrigerated cavity, and they are essentially trying to tune their detector, like an old radio, to find the frequency of the axion and hear the faint hum of it converting into light. It's a long shot, but the search is on. And there are other, even more exotic ideas. Sterile neutrinos, primordial black holes, which are not made of normal matter but could have formed from pure energy in the chaos of the Big Bang. The list of candidates is long and creative, but there is another possibility, a more radical one. What if there is no dark matter particle? What if the problem isn't that there's missing matter, but that we are wrong about gravity? This idea is known as MOND, for Modified Newtonian Dynamics. It was proposed in the 1980s by an Israeli physicist named Mordechai Milgrom. He noticed that the problem with galaxies always appears in regions where gravity is very weak, like the outer edges. So he suggested that maybe Newton's law of gravity itself is wrong in these situations. Mond proposes that at very, very low accelerations, gravity is actually stronger than we expect. This extra pull would be enough to hold the outer stars in their orbits without needing any dark matter. It's a simple, and in some ways beautiful idea. For individual galaxies, it works remarkably well. In fact, it often makes better predictions for galaxy rotation curves than dark matter models do. But MOND has big problems of its own. While it works well for galaxies, it doesn't work nearly as well for larger structures, like galaxy clusters. It can't explain the bullet cluster, where the mass and the normal matter are clearly in different places. How can you separate gravity from matter if gravity is just a property of matter? Most importantly, MOND can't explain the cosmic microwave background. It's fundamentally an ad hoc fix for galaxies, not a complete cosmological theory. So we are stuck in a strange place. We have two main ideas. The dark matter hypothesis works beautifully on the largest cosmological scales, but has some nagging problems on the scale of individual galaxies, and we can't find the particle. The modified gravity hypothesis works beautifully on the scale of individual galaxies, but fails on larger scales and seems to be in direct contradiction with evidence like the bullet cluster. This is where science is today. It's a field in a state of creative tension. The easy answers have been ruled out. The leading candidate, the WIMP, is on the ropes. The radical alternative MOND has its own serious flaws. Maybe the answer is a combination of things. Maybe there's a new type of dark matter particle that has some self-interaction, which could explain some of the small-scale issues. Maybe there's a more sophisticated version of modified gravity that can explain everything. We don't know, and that's what makes it so exciting. This isn't a failure of science. It's the opposite. It's science working exactly as it should. We have a profound mystery, and we are poking at it from all sides. We are building bigger and more sensitive detectors deep underground. We are pointing more powerful telescopes at the sky. We are smashing particles together with more energy than ever before. We are pushing the boundaries of theory and technology. The search for dark matter has forced us to confront our own ignorance. We look up at a night sky filled with stars and galaxies, and we have to accept that we are seeing only a tiny sliver of reality. The universe is dominated by a substance we cannot see and do not understand. It is a humbling thought. Whatever dark matter turns out to be, finding it will revolutionize physics. If it's a new particle, it will open up a whole new dark sector of particles and forces, a parallel world that interacts with our own only through the gentle tug of gravity. It would be the biggest discovery since we figured out the atom. If it turns out to be a modification of gravity, it will mean that Newton and Einstein, two of the greatest minds in history, didn't have the final word. It would rewrite the very laws of the cosmos. Either way, we are on the verge of a new understanding of the universe. The detective story continues. The clues are all around us, written in the motion of the stars, the bending of starlight, and the faint glow of creation itself. We just have to be clever enough to read them. The one thing we know for sure is that the universe is far stranger and far more mysterious than it looks. And the truth is still out there hiding in the dark.